Good afternoon, everyone. I am Romit Kaware, and I've been working on this aspect of sediment management within the tropical waters for over 2 years now. So, I'll we'll have a discussion more about our what work we do pertaining to the sediment management. I'll start with an general introduction first. We see that the Indian Ocean region is a very contested region today, especially within the current with the current scenarios of what we have seen in the Strait of Hormuz, and also we know that a lot of oil shipping lane, more than 60 to 70% of the global oil passes through this Indian Ocean region. So we see that there is a lot of interest of the major global players within the Indian Ocean region. There have been a lot of activity of the Chinese as well, serving the seabed in the Indian Ocean region. It poses a very geostrategic importance. Now, being so much of geostrategic importance and being the third largest ocean, it still remains one of the least surveyed and least sampled oceans. Primarily because again, most of the Indian Ocean region countries are low to low middle GDP income countries. So again, most of the ocean exploration requires a lot of funding, and such kind of oceanic exploration equipments and vessels are required. Again, the being the least studied and understanding how the various vessel movement, the shipping movement affects the sediment transport, or how the seabed is dynamically changing with all of the oceanic conditions, it becomes very much crucial. Especially when I talk about the Indian condition, we have very paradoxical situation when we talk about the sediment related challenges. So every monsoon, we have a lot of flooding in an rivers as well. We have the Ganga Brahmaputra river system, which carry about 1 billion tons of sediment into the Bay of Bengal annually. Now, this brings in a lot of sediment flux within the Bay of Bengal into our coast. Now, another challenge is that these sediments also originate from the right up from the Himalayan mountain ranges. Now, while these flow right from the Himalayan through the Gangetic Plain and enter a Bay of Bengal, they might also get trapped in some dams, in some reservoirs as well. In fact, a recent study by ISER Bhopal tells that many of our aging dams face a very issue of storage reduction, and saying that some of our reservoirs might have actually 30% of reduction in storage capacity due to this excessive sedimentation. They also trap sediment. So at one place we have excessive sediment coming into our coast. At another place they are getting trapped within our reservoirs as well. So we have to look into the various nuances of how that sediment flow and that sediment entrapment is occurring. As you can see in this schematic as well, the thickness of this sediment within the Bay of Bengal region is one of the highest in the world. So it poses a very high sediment flux into the Bay of Bengal or into the Indian Ocean, which requires us to have a very unique understanding of what the local conditions are there. From this context, what we are trying to see is understanding how the sediment flow is happening, or how are we going to manage the sediment. That is looking how the source of the sediment, what is the source of the sediment, and based on what factor it is going to move, it is going to accumulate or get deposited in the various river system, coastal systems, or the marine ecosystems. And especially these need to be understood within our very unique dynamic tropical conditions, so that we are able to come up with some region specific solutions. So this is where we talk about the UDA driven sediment management. In the UDA driven sediment management, we mostly talk about how we could have this data driven decision support, where we could have data from multiple sources, the hydrodynamic data, in situ measurements, the acoustic data, satellite data. So I'll talk about more of this later on, but how we can integrate the data from the multiple sources. And once we have that integrated data collection, proper data analysis has been done, how that can actually help us in making proactive sediment management plans rather than having reactive measures itself. Uh, so uh, when I talk about the sediment management, it becomes very crucial to understand what are the tropical challenges. So the first is that the Indian Ocean region, or the Indian subcontinent itself, it has very high sediment load. A lot of sediment is getting deposited from the Ganga Brahmaputra river system itself. Uh, in the meanwhile the various natural and the anthropogenic activities as well. So we have if there might be rampant deforestation or rise in agriculture, how that land use pattern changes the amount of sediment that actually goes into the freshwater systems. That leads to a change in the sediment load as well. How that sediment load then transports right from the starting from the mountain ranges into the Gangetic plains, how the Gangetic plains are affected by that sediment flow, and then what are the different kinds of sediment within that flow regime that needs to be crucially understood. Apart from that, we also have a very rich biodiversity within the Indian Ocean region as well. So we need to look into how that changing sediment pattern and the constituent of the sediment affect the diversity as well. At the same time, we also need to look into how these biological activities also affect the various acoustic signatures that are very crucial in the acoustic based sediment classification. So there could be biological noise from this various kind of benthic ecosystem as well. Then apart from that, we all know that the Indian Ocean region is a very major shipping lane. It has a lot of anthropogenic activities of continuous shipping, dredging, trawling. So again, how those activities affect the sediment transport, or what are the effects of, say, the vessel movement or the propeller movement on the actual sediment deposition patterns. This needs to be understood so that we are able to look into holistic pictures. Moreover, the acoustic noise from the various of propellers also reduces the signal to noise ratio as well. So again, it has effects on the acoustic part as well. Now, when I talk about the acoustic sediment classification itself, we also need to look into that this uh, Indian Ocean region exhibits strong diurnal and seasonal temperature and salinity gradients as well. Now, uh, this gradient again not only affects the speed of sound, which is very much crucial for the acoustic propagation, which is required for the sonar working for the bathymetry related applications. One of the major challenges is that the tropical condition or the tropical waters behave as acoustically shallow. Now, what I mean by acoustically shallow is that the SOFAR channel depth. So the SOFAR channel is a channel which leads to very slow speed of sound and a long range acoustic propagation. Now, this SOFAR channel within the tropical conditions might range from depths of 2000 meter to 3000 meter, while the uh, while say in other regions the normal range is around 1000 meter, or it ranges up to 50 meters at the poles. So you see, even we in order to have that large long range acoustic propagation, we need a further more depth than as compared to other regions. Now, our own sonar systems might not be capable to actually go to that deep layers, again limiting the proper propagation of acoustic communication. So here also we can see that that the sea surface conditions of temperature and salinity vary a lot, especially when we talk about the sea surface salinity between the Bay of Bengal and the Arabian Sea. We can see a stark difference. Now, this might be accounted due to a lot of freshwater river systems are getting uh, uh, they deposit their own freshwaters within the Bay of Bengal, the eastern flowing rivers. So that might lead to a decrease in salinity there. But we need to really consider how this change is happening within our own uh, uh, environment, within our very own environment, how these local changes affect. Uh, Another major is the species distribution. So as I mentioned, we have a lot of coral reefs, the marine protected areas within the Indian Ocean region. Uh, how the sediment flow or the sediment type affects the benthic ecosystem in all. What are the different, if any vessel movement is there, how that affects the sediment flow, and that might lead to redistribution of some pollutants or of some of the marine debris that might affect the benthic ecosystem. So all of this needs to be properly understood, of how the benthic ecosystem, the environment, the anthropogenic activities, all of them are tied together, and that's why we are looking to study all of them. And one of the major part that we need to look into is that the Indian Ocean region countries, uh, they host around 30 to 35% of the global population, and it's a very young demographic. But we see that they lie in the low to low middle income profile. So we again, a lot of money can't be put into the oceanic research and development. So we can't just have very expensive solutions imported from, say, the Western economies, and that can be used directly. So we need to develop some region specific, scalable, adaptable, and affordable solutions that might also leverage uh, human uh, the human resource within the region itself. So what happens when we actually have some of the sonars which are mostly being imported from the more advanced economies. Now when they are calibrated within their own conditions. Now when such equipment is being brought and deployed in their own Indian the tropical conditions, there might be added the propagational variability of the sound signal due to the anthropogenic noise, due to the biological noise itself. So that noise interference affects the signal to noise ratio, and then deploying them, calibrating them, and maintaining them poses more of the logistical and technological challenges as well, when they are not properly maintained, and due to the high or due to the larger depth of the SOFAR channel as well, to uh, the overall efficiency of the sonar systems effectively reduces to just 60 to 70%. So we have to pay more for the solutions with, and we are getting in return very less efficiency as well. Now this gives us a very good background to basically understand what our local conditions are, and then based on them we can come up with our own technology, our own technological solutions, so that we can improve the efficiency. uh, so this is where we study the sediment management. So what we have done is we have divided sediment management into two different dimensions. So the first dimension talks about sediment transport, where we look into the transport of the sediment across various domains of, say, rivers, oceans, and reservoirs. And then the other is the sediment classification, where we look into how that sediment classification has applications. I'll explain a bit more later on. And then these are mostly considered within the coastal zones and the freshwater systems. Now, why we are looking differently for the coastal zones and the freshwater systems is because of the differences that lead to the sediment transport and other depositional mechanisms. So in the coastal systems, the driving forces of that sediment would be waves, tides, currents, or any kinds of cyclones that might lead to the very extensive sediment transport. Now, this leads to a lot of littoral drift, and might affect the shoreline erosion. Ports, the navigational channels might be affected. So we have to look at sediment management from a totally different perspective, talking about the coastal erosion or what would be the navigational related challenges there. In case of freshwaters, we are mostly talking about how the river flow or the river discharge actually or the rainfall actually affects the transport of the sediment. So we are mostly concerned with the bed load concentration or the suspended load concentration. We look into how the riverbed morphology affects, or riverbed morphology, or the discharge or the flow velocity or the turbulence affects the sediment transport. Here we are mostly concerned with the or the sediment management within the dams, the reservoirs, or the inland water systems as well, facing challenges of excessive siltation, storage loss, and urban flooding itself. So the coastal zones and the freshwater systems, they both have very unique condition that needs to be separately studied. Now when we talk about the sediment, what is the role of sediment itself, the sediment characteristics, how do they affect the transportation and classification itself? With this again, the sediment transport and is governed by the sediment classification itself. So we could have different kinds of sediment: clay, silt, sand. They might again vary with the texture as well, their roughness, what would be the cohesiveness. There might be some more cohesive sediments, there might be cohesionless sediments. So these characteristics, these mechanical properties actually define how this sediments may be transported across the across the fluid medium itself, how the hydrodynamic conditions and the sediment properties are actually interconnected with each other. We might be able to get it from the sediment classification itself. As we can see, the cohesive sediments, they might be able to flocculate together and they may settle earlier, while the cohesionless or the coarser sediments might flow over through larger distances, and then they might settle down, say near the inlets of the estuaries or further on. So again, sediment characteristics play a very crucial role, this requiring proper sediment classification. Now, when I talk about the two new one or the two dimension of sediment management, the first one is the sediment transport modeling, where what we actually do is we take in the various input data parameters, like what is the sediment type, what are the flow conditions of the river flow conditions like velocity, the discharge, what are the sediment properties, what are the bed conditions, the bed roughness or the slope, and what are the various different boundary conditions there. And then we try to solve some physics based equations, like the Navier-Stokes equations are there, some FEM, through some FEM or FDM methods, so that what we are able to do is, given the input conditions, we are able to predict or we are able to model how the sediment transport flow would look like. We could have certain dynamic heat maps of where would the sediment where would be the excessive sedimentation happening, or where are the shoaling happening. Now, to model this, there are a lot of commercial softwares also available, like the Hecras or Delft 3D is there, uh, through which we can model the sediment transport. Right now, we can also leverage the machine learning and AI based techniques to actually model sediment in case of the lack of proper data. This is what we are also looking into. The second aspect is the sediment classification. So in sediment classification, we have to generally what we do, conventional methods actually require you to go to the particular location, pull out some grab samples, and then do extensive laboratory tests to find out what are the mechanical properties or the chemical properties. What other approaches can be is to have the satellite based sediment classification or the suspended sediment concentration mapping. uh, through the various satellite systems like the Sentinel or the Landsat satellites, we can extract the satellite imagery or the spectral data. Now, there are various empirical relationships also developed through which we can relate the various spectral data to the suspended sediment concentration or to the turbidity. Uh, a lot of spectral indices are being developed to actually map this satellite information to the suspended sediment concentration. So it provides a very macro range, as we can go over from a very large spatio-temporal range to actually classify the sediment with varying timescales as well. The another technique would be the acoustic sediment classification. So here we would have the different acoustics, like the various sonar systems like the multi-beam echo sounders, a sub-bottom profiler, or the side scan sonar. And then but by choosing a particular frequency, we can actually try to gather the backscatter data. Now, once we have the backscatter data of the various set of the seabed, we can try to have proper data analytics on or analysis on them, so that we are able to actually extract meaningful information from them, creating sediment type. So I'll explain what would be the different methods for this acoustic sediment classification in the end. But these are the two major techniques that can be leveraged to have a large spatio-temporal sediment classification itself. Now, when I talk about the sediment transport or the sediment classification, we really need to look into where all of this, practical applications might go into. So, one of the major challenge that the Indian coast face is shoreline erosion. So around 40% of the coast face erosion of some sort, mostly in Kerala, Gujarat, Tamil Nadu, West Bengal as well. So with how the changing hydrodynamic condition leads to the shoreline or leads to erosion and accretion of the sediments. Now, once that erosion and accretion happens, how that sediment gets redeposited? If say there is a nearby port, how that shoreline erosion affects the breakwaters, how it affects the foundation of the birds, or if that sediment is redistributed to the navigational channels, or how is that sediment is getting redistributed into that navigational channels. So we need to have these studies of how the shoreline, what are the sources of sediment there, how the sediment is getting redistributed to the various natural forces as well. Now, say such sediment goes on depositing into the navigational channels of the ports, and it remains unchecked for a longer period of time, as you can see in the graphic as well. If it goes unchecked, it might clog the navigational channel itself, uh, thereby reducing the thereby reducing the available draft for the larger vessels and reducing the operational efficiency of the ports itself. So what's the a conventional solution? Dredging is one of the most conventional solution that they have taken up for sediment removal. However, we must acknowledge the fact that dredging is not a react, or it's not a should not be a short-term solution itself. We need to look into long-term solutions of how are we going to actually reduce the sediment supply itself. Also, when I talk about dredging, how we do not have the understanding of the local sediment dynamics. Say if we have done dredging over a particular navigational channel, how are we actually mapping the pre and the post dredge volumes? So there is no proper compliance of the dredging volumes itself, and how that dredging affects the seabed, the benthic ecosystem. Again, understanding how the sediment transport might happen, or how the sediment flow change due to the dredging itself affect the benthic ecosystem, leading to a more extensive environmental impact assessment can be added. Now, here our sediment transport modeling and our predictive modeling can actually help. So if we are able to identify what are the various sources of sediment in cases of extreme hydrodynamic condition, in cases of extensive flooding or cyclone events, how the sediment flow might happen. If we are able to create a digital twin of the port itself and then model the sediment flow changes for different conditions, we might get hotspots. So, and then we can go into the particular hotspots and then take up uh, uh, solutions for that region itself. So what we are trying to do is going from a macro scale to a micro scale response. Now, as I mentioned, the dredging operations are being extensively used. In fact, when setting up a new port, 30% of the cost can be taken up for the dredging itself. But if we are not able to manage this, what is the dredged amount, or we are not able to quantify the dredged amount, it leads to a lot of operational inefficiencies as well. Because if we go over dredging, it might have issues with the seabed, the benthic ecosystem as well, leading to a lot the environmental impact as well. If there is under dredging, then we might need to do repetitive dredging, again leading to higher cost itself. So it's a very inefficient method of monitoring the dead sediments. At the same time, when the sediments are getting redistributed, they might release some of the toxicants, and also lead to an increased turbidity. Now, this increased turbidity might affect the sunlight transfer or propagation within the lower regions of the seabed itself. Now, uh, when such sunlight is hindered from entering the seabed itself, it might lead to eutrophication as well, leading to some dead zones within the water bodies itself. Not only coast, but when we talk about reservoirs in case of large water bodies itself. So if we are not properly able to link the amount of dredging with the environmental impacts, or even if such dead zones are created, it might affect the overall livelihood of the fishermen or of the coastal communities which live near the coasts. So it not only has environmental impacts but also the socio-economic impacts as well. So we really need to look into the coupling of the people, the economy, and the nature all together when we are talking about the sediment management. Now, again, this sediment management has importance in the inland water transport as well. So, in order to have proper navigable waterways throughout the year, we need to have some certain draft over the year. Now, excessive sediment supply from various sources, or say from floods, or if water is released through the dams, how that affects the sediment supply. Uh, uh, that needs to be really looked into. So when I talk about this sediment trapment by the various uh, reservoirs, we are concerned with the watershed management. Now what might happen is that a lot of large reservoirs or dams on the river systems might entrap these sediments. Now this entrapment leads to the storage capacity, but it also can endanger the structural stability of the dam itself. uh, in fact, the most of this entrapped sediment, if that is getting redistributed, it affects the water quality as well. Now if that sediment contains some metal pollutants or some heavy metals, how that affects the water quality and the benthic health. Now this might also affect the human health as well, so it has far reaching consequences, just rather than just the turbidity. So we really need to look into that environmental impact. And also, if the dams are entrapping the sediments at the upstream, they lead to sediment starvation downstream. So how that sediment starvation downstream is affecting the downstream morphodynamics or the downstream aquatic systems, again, so this also needs to be properly understood. Now, one of the I'll talk about one of the cases that disasters that happened. So this was in the 1980s in the Lake Pegner. So they were doing some oil rigging, oil drilling was done within the lake itself, and one of the drilling actually penetrated a salt dome. So there was an salt mine underneath, and it penetrated a salt mine, which led to a catastrophic creation of whirlpool, and all of the freshwater lake drained into that salt mine itself. Now, interestingly, the fresh water from the lake was drained, and it was replaced by by the salt water from the Gulf of Mexico. So you see that, not knowing what lies beneath the surface, beneath the seabed, it costed the change in the ecosystem from the freshwater to the marine to the saltwater ecosystem, affecting the aquatic ecosystem there and the nearby ecosystem as well. So that's where we are laying emphasis on the seabed mapping itself. So within the complex or the rugged terrain or the rugged bathymetry of the Indian Ocean region, we need to, when we are talking about we need to look into what is the bathymetry look like. And also, when we talk about the earthquake fault zones, we need to look into how the various earthquake related or the tsunamis or the vessel movements actually affect the sediment stability or the flow of the sediments. This has very much applications in planning of the undersea cable route. So we recently have the undersea cable from the Indian mainland to the Andaman and Nicobar Islands as well. So how that risk assessment of these undersea cable routes would be done, sediment classification might come into the picture. Also understanding the polymetallic nodules, where in the central Indian Ocean basin we have the polymetallic nodules. So uh, uh, if the sediment classification can help us in mapping the spread of these polymetallic nodules, that can be very that can be crucial as well. Another major application is understanding the sediment bearing capacity. Now sediment bearing capacity is actually the maximum load that can be taken by the sediments before any excessive settlement or failure happens. Now this is actually calculated based on what is called the bearing capacity factors, and these bearing capacity factors are based on what is the type of sediment, whether the sediments are do they have more friction, or what is the type of sediment, it's a silt, sand or clay itself. So the bearing capacity is affected by the type of sediment itself. So if you are able to link the results of the sediment classification to the sediment bearing capacity, these have various applications. Also, if we look into what is the sediment transport near the pile foundations of the various bridges itself. So we have the bridge piers. If they are subjected to a lot of local scour, that is a lot of erosion happens, so that it affects the foundational stability. In such cases, there might be a differential settlement of the bridge itself. So there have been cases in Bihar itself where due to this covering, there is this differential settlement, endangering not only human lives but the infrastructure damage is a lot as well. Now, this kind of sediment bearing capacity can be useful in the construction of offshore refineries, wind turbines, say the various ceilings can also be, the foundation design is also affected by this sediment bearing capacity. So if we are able to have an initial estimate or an initial dynamic mapping of the sediment bearing capacity, uh, that gives us a good estimate of having proper planning. Apart from that, the major application also lies in the strategic resource deployment. So in case of deploying heavy equipment, we know the sediment bearing capacity, initial estimates of sediment bearing capacity, we can get an understanding of what is the maximum load of the equipment that can be taken by that particular soil itself. Also, say when we need to have trenches in a particular soil, understanding what is the type of sediment would be very crucial in defining what would be the depth of trenches or the dimensions of trenches itself. This also finds its applications in having this mobile bridging equipment and in amphibious operations as well. So, say in regions such as Sir Creek, if we need to deploy such bridging equipment, we really need to know what would be the maximum load that the soil can sustain without failure. Again, if we could, using the remote sensing methods or the acoustic methods, if we could have a mapping, a large scale mapping of or a heat map of the sediment type, of the sediment bearing capacity, it helps in the proper tactical planning itself. Another application is in the benthic ecosystem monitoring. So the benthic ecosystem are the or is the flora fauna which resides in the lowest most part of the seabed. Uh, if we are able to relate how the sediment flow, what is the sediment type, and the sediment constituents actually affect the benthic ecosystem health. So if we are able to uh, uh, integrate the sediment classification data with the environmental parameters, the species distribution itself, we might be able to look into what is the benthic ecosystem health, leading to a proper environmental impact assessment, especially when we talk about the fisheries, the aquaculture, or the coral reefs as well. Another major application comes in the abiotic element detection, where we can use the sediment classification techniques like acoustic sediment techniques to look about the marine, what would be where is the marine litter, or we can map the ship debris, so that the navigational is secured. We can also use this to uh, actually have understanding of the seabed, so that the in cases of say underwater mines, are we able to detect the underwater mines through the sediment classification. So this abiotic element detection can also be a very crucial application. So coming up with how our sediment management techniques of our sediment classification and transport can be actually useful is, say for example, we have a particular location where dredging needs to be carried out. If we have the satellite data, if we have the acoustic survey data along with the hydrodynamic data, and then we are able to process that data, what we can do is, if we are able to find using the acoustic data what is the different sediment types and what are the thickness of the layers of these different kinds of sediments. So if we are able to map the thickness and the type of sediment, we can be able to have a good estimate of the volume of the sediments. So we can do this exercise pre-dredging and post-dredging to identify what would be the amount of dredging, that amount of sediments that are getting dredged. Understanding what is the sediment types actually helps us in a proper in having proper dredging techniques, whether hydraulic dredging or mechanical dredging is required, or even when the dredging is done, these sediments can be reused again. If the sediments are have proper mechanical properties, these
Romit,
can be
two
used.
more minutes for you. Huh?
Yes sir, yes sir. So if the sediments can be used again. So again, this has also has proper applications in the disaster risk management as well. So if we are able to have proper idea of the pre-flood level and the post-flood level, we can integrate this various sediment parameters, the flood levels as well within the disaster management plans itself. So what we are actually planning is that we have this multi-data source integration, so that we have proper integrated with the local knowledge as well, so that we have evidence-based planning. Now, the major challenge that lies is that we have, even though if we have data from various sources, there is no single platform to actually connect these various data. There might be data reliability issues, formatting issues as well, and there might be issues of data sensitivity as well. So, how are we going to go about it? Here, our major contribution comes where we have UDA-driven approach, where we integrate all of this data together within a combined marine spatial planning framework. So we could have different data parameters stacked together, and then uh, we could have this data within a particular this marine spatial planning. We could have real-time data analysis running in the back end, so that we could make data, proper decision-driven systems as well. Now, these systems are not only scalable but can also be adapted to different conditions. So, for freshwater, for coastal systems, for lakes, for estuaries, this marine spatial planning type framework can be adapted to different conditions as well. So, what our approach is basically is, for a particular region of interest, we have proper field validation using taking actual sediment graph samples. Acoustic sampling is also done apart from the remote sensing based data. Now, once we have all of this data and understanding what are the pressure, temperature, the salinity measurements within that particular medium, we can go on to having this proper pre-processing, post-processing of data, including noise filtering algorithms, or employing some mathematical models, so that we are able to extract data from the raw acoustic and the sediment data, and that can be fed into an analysis tool where in real time we would be able to see the correlation between different parameters, or the heat maps, and then that can be used to make again proper decision making under various, and we can actually be able to map the flow of the sediment under different hydrodynamic conditions itself. Now, these are some of the case studies that we have taken up. This was taken up in the Khadakwasla Dam, so that we are able to validate the acoustic-based sediment classification. So here we had the various acoustic systems like the sub-bottom profiler side scan sonar deployed on the ships. Apart from that, we also took the CTD measurement, that is the salinity, temperature, pressure measurement, so that we are able to map what is the speed of sound within that particular propagation medium. Using this data along with the raw acoustic data, we applied some noise filtering techniques, fast Fourier transforms as well, and then we employed a model called the reflection coefficient based model. We are taking use of the reflected and the transmitted energy of the sound of the acoustic waves. We were able to map the reflection coefficients. Now, these are unique for certain kinds of sediments, and so we were able to deduce that most of the seabed sediments are of the type of silt and sand, clay and silt. Now, this was validated by our laboratory experiments as well, that most of the sediments are of silty clay type. A similar thing we are doing for Ujjaini Reservoir itself, but apart from acoustic survey, we are also looking into the remote sensing and a larger environmental impact assessment as well. So currently we are going through the remote sensing or capturing the satellite imagery for the Ujjaini Reservoir, and we have also created a plan for the acoustic sediment classification for the Ujjaini Reservoir itself. Another work that we have done is the urban flood mapping, where we have taken use of the digital elevation models, the and the rainfall data to see under different conditions how the sediment flow might happen, or how what would be the extent of the flooding under the extreme conditions. So this also helps us in having some large scale disaster management plans ready. So finally, to give you the whole larger picture, see, in the Brahmaputra region, we have a lot of sediment influx, and it leads to a lot of challenges. Say, bank erosion is there, the path changes, the river path changes. So, how our acoustic and the remote sensing solutions can actually help us is to have proper continuous monitoring over a large spatio-temporal range across various discharge conditions, flood conditions, and flow path changes, and then we are able to link them to the sediment classification, to sediment transport, and then creating a proper AI-based prediction tool, so that under different conditions we might get, okay, so these are the sediment parameters, or this is the flood level, or the sediment concentration under different conditions. And so finally, this needs to be looked into in case of, say, the port development, the freshwater systems, the benthic ecosystems. So all of these are linked to sediment management. So there is a very larger picture that we are trying to solve currently. So I think, yeah, that's it from my side.